So here is the definition of the word, or the axiom governing this word. Every point has exactly 3 neighbors, and you could also have the same thing, exactly 3 neighbors, and you can have except
this time
whatever.
I need 3 points? Except 3 points or except?
No, every point has exactly 3 neighbors with the exception.
Except for 3 points, I think. Or how many points will you need?
Well, we will specify some condition.
Yeah.
Let's see, but let's look at this one.
Yeah. So let's create a world like that. So let's go the same way we put a point down, and let's add 3 neighbors to it.
Okay. So that this condition is satisfied by this object.
Yeah. So now if you say every point has exactly 3 neighbors apart from 3 points which have 1 neighbor, then this is this one.
Yeah, but 3 points are allowed to have
1 neighbor.
1 neighbor or 2?
This one has 1.
Yeah, okay.
So that's this.
Yeah, that's right. Okay.
One easy way to make it 2 is just to do this. So 2 points. No, then it's exactly more complicated. Now, if we want to create this word, every point has one easy way of doing it is just to close this.
Okay, then it is the first one, the exception clause.
It's an example of the first one. There might be many other ways to build this, but this is one.
Can you make this bigger and satisfy this condition?
Can we make this bigger?
More points, yeah.
So how about no, this is 3 neighbors. We need to remove.
Yeah, we may have to remove all of those because you can't. Yeah.
So let's start with this.
Yeah. This one.
Yeah, and we'll take this. This now has 2 neighbors. We can take this point here, this point here, and in fact we can close it.
So this has 3 neighbors, this says
this has 2 neighbors. This has, these 2 have 2 neighbors, so now we need to
okay.
And now this has 2 neighbors.
This one has 3 neighbors.
Yeah, but this one has 2.
This one has 2. Okay.
So we need to take this out.
One more, yeah.
And actually is this
that's still going to be slightly difficult. Right.
No.
This says wait, not maybe.
No, this one has 2 neighbors. And we do the same here.
Wow. That took some doing.
Yeah. But it's a larger world with every point having 3 neighbors. I think we should recheck once.
Yeah.
This point has 3 neighbors, this has 3 neighbors, this has 3, this has 3, this has 3, this has 3.
Yeah, it looks like everything
looks
is
like it works.
That's actually all that we did was to say 3 neighbors, and even for us to figure out
what that world
how
looks
to
like.
create the objects in this world, it took some effort.
Yeah.
And you can create all kinds of interesting words by saying 4 neighbors and other kinds of conditions.
Yeah.
So in this world, what's a circle? What's the smallest possible circle?
So every point has 3 neighbors. So smallest possible circle with
3 points.
Will be with 3 points. This.
So if you have A, B, C, that's a circle
with this center.
But that is the center.
Yeah.
How about 2 unit lengths?
So here this is 2 unit lengths. So let's take the same center. This is 2 unit lengths. So let's do P1, P2.
And this is the center.
Yeah.
Okay.
P3 and P4.
Huh. Okay, that's very interesting. Have you included all of them? 1, 2, 1, 2, 1, 2, 1, 2, 1,
2.
2. That is the same thing. 1, 2. That's already okay. Very
So
interesting.
This has 4 points. What about, let's say, 3 units of distance?
Okay, I think we should erase some of them, otherwise we're going to get very confused.
Yeah.
So I'm going to erase these things.
Yeah.
So this is the center. Center I'm going to call it C. And 3 unit length circles.
Yeah. 1, 2, 3.
Okay. So that will be P1. Okay.
1, 2, 3. Once again, we read
Yeah.
P1. 1, 2, 3. Ah, that's interesting because it's both 1 distance away and 3.
So is that
P2.
and I'm going to put a question mark here.
Yeah.
Yeah.
1, 2, 3.
Yeah.
It has 3
But again,
points.
1, 2, 3, 4.
3 during the distance 3.
No, but if you take some other path,
The distance is 3. So 1, 2, 3. This is P4. 1, 2, 3. This is P5.
wait, this is the center.
Yeah.
If I take this path, this is 1, 2 units, not 3 units.
3. This one is 3.
That one is 3, but
Yeah.
this one.
But this one is also 1, 2, 3.
But if you take this path, it is 2.
But if you take this part, it's 3.
Yeah. So this is not. This doesn't seem to be straightforward.
It's not
There are some
straightforward.
complications.
Because one really confusing one is if you take something which is 4, if you allow the circle with 4 unit length, then 1, 2, 3, 4. The center is
Back
part
to-
of the circle. By
Okay.
So
Okay.
we need to be, either we need to allow that,
Alright.
or we need to have more clarity on our definition
Of a
circle.
definition.
Yeah.
Okay.
Maybe it has to be the straight line path has to be from the center to that point has to be of that value.
Right. So you get a shortest distance.
The shortest
path
distance
must be.
that.
Okay. In which case, if you go this one, this will be the shortest.
Yeah.
So this
So
doesn't count.
this won't be part of the 3.
Right.
Only you only get this and this. You only have
Yeah.
2 points as part of the 3.
So this looks like a very interesting terrain for independent investigation for all students.
Yeah.
It will be extremely interesting.
Yeah.
Okay. So I get a sense of how you create mathematics. You create worlds and then define things and come up with theorems.
Yeah. So I guess we can leave it to people to work on the
Yeah.
4
4 and 5 and various kinds of
Yeah.
constraints that you can put them. And then you can say, can a circle be a triangle?
Yeah, so 4 neighbors actually is kind of interesting because that's basically your graph paper.
Right. Oh, okay.
If you're allowed, if their diagonals are not
Yeah.
neighbors.
So if a graph paper looks like this,
Yeah. So
And-
if it's an infinite world, it'll be graph paper.
so there is a point here, there's a point here, and there's a point here, point here, point here, and point here, point here. But these two are not connected.
yeah, but that's only if it's an infinite world, it'll be a graph paper.
Yeah.
If it's not an infinite world, you'll have to somehow connect these sorts of things, and it'll
Yeah.
be some messy thing like this once again.
Yeah. So in a graph paper, this is the graph paper. Obviously, this one will have only 2 neighbors, and this one will have only 1, 2, 3 neighbors.
Yeah.
Okay. So again,
Yeah.
students can experiment with all those geometries
Yeah.
and figure out what kinds of theorems would emerge.
There's interesting questions which come up for 4, 5, 6 and beyond. Is that can you create such a world? Can you create a world with a finite world with 4 neighbors?
Some of them it may be impossible.
In some it may be
Yeah.
impossible,
Right.
and it may be impossible if you on a flat surface. Maybe if you put it in 3 dimensions and you're allowed to go behind and under things, it might be more possible.
Yeah.
So these are all considerations which need to be taken.
On TV screen, when you have each pixel, they represent like a triangle. I've seen that happening.
Yeah, yeah.
So I don't know exactly what happens. So it looks like this is the kind of geometry that you need. Pixel geometry seems to be.
Pixel geometry is
Is a discrete geometry.
each thing has how many neighbors? I think 3.
I don't know how many.
4,
3 is it?
5, maybe
Yeah.
more. iPad, whatever.
We'll have to find out.
Yeah.
Again, that will be something interesting to
Yeah.
explore. Okay. So
Yeah.
So shall we give it back?
So what we did here was in earlier videos what we were doing was working within a theory.
Yeah.
We worked within Euclidean geometry. We worked within number theory. Now
let me write that down. So what are the kinds of things that you can do in mathematical inquiry? So you said something like, one is within a theory, okay, you come up with conjectures.
Yeah. You prove them.
Conjectures, you prove them. Is there anything else that you can do within a theory?
Maybe
apply them.
Apply them.
Yeah.
Apply theories.
Apply the theory to the real world. Model.
Then create theories is the second thing you can do.
So the second thing that you can do is create theories.
So usually how you do that is either you come up with something, you're very imaginative and you come up with something, or like we did, you tweak certain things. Rather than saying an infinite number of points, a straight line has an infinite number of points, you say a straight line has a finite number of points. You change
That's what we did actually in the case of you took Euclidean geometry
and change something.
Change one thing.
Yeah.
Okay. So this means you can create a new theory by modifying
existing theory.
Existing theories. Modifying an existing theory.
Or by just being very creative and coming up with something. Usually how that is done is through something you see in some interesting problem you see in reality.
Okay.
So for example Euler. Many people may have heard of the bridges of Königsberg.
When you say Euler, is this
Yeah. Yeah, not O-I-L-E-R. Yeah.
Okay.
Yeah.
So this is not now just Euler, this is Euler.
Euler.
Okay.
So Euler had this interesting problem of about bridges. You can take a look at it. It's everywhere on the internet.
Bridges of
Königsberg. K-O-N-I-G-S B-E-R-G, I think.
Okay.
In order to solve that problem, he had to create something called graph theory.
Okay.
Which is a mathematical theory.
Yeah. So you create objects and you create laws governing those objects.
So definitions and axioms.
This is axioms. That will be much more ambitious.
Yeah.
This is a
little bit easier to do.
But even then, as we saw just now,
Yeah.
the results can be quite startling.
Yeah.
Even if you change a small
Simple things, yeah.
Yeah. So we'll invite you to do this as well in addition to this.